Hello and welcome to this online training. I am happy that I have you here today. My name is Daniel and I will be the presenter of today's online training. Today is the last part of our online training, RFEM 6 for students. We will do the timber design together and I'm very happy to show you more about RFEM 6 and the possibilities regarding timber design. To me, my name is Daniel. I am the COO of Dlubal Software and mainly responsible for our human resource part and also marketing and sales, and I will be the presenter today. Next to me is also Jürgen, who will support me today. Jürgen, could you introduce yourself, please?
Yes, of course. Hi, everyone. My name is Jürgen, and I'm working for Dlubal Software as a technical support engineer. So I answer all kinds of questions via chat, email, or telephone. And if you have anything on your mind today, any questions, don't hesitate, ask them in the chat or ask a question. I'll be happy to help you.
Perfect. Thank you very much, Jürgen. Let's go deeper into the whole topic. So I will stop sharing my webcam and in order to show you more of our presentation. So for those who are attending the webinar or the training for the first time, here a few words about the platform. GoToWebinar. You can show or hide your control panel here by clicking this arrow. On the right side, you find some audio settings where you can adjust your loudspeakers. And as Jürgen already said, you can ask us every question you want. We will answer them as good and as fast as possible. So, training series RFEM 6 or also our section for students. Today, the last part, timber design. And what can you expect from today is that we go through into a kind of introductory example. So we will model and design a timber column. The next thing will be the definition of design supports, and I will show you also how to model and create a notch. Then we will design a Duopitch roof, and finally we will end this training with a truss in timber. Okay, so let's jump right into RFEM 6. I'm very happy to do this now with you. Before we start, I have prepared a short poll in order to give me an overview about your experiences regarding timber design. So I will launch this and please answer that. Okay, the most of you have voted. I will close this poll, share the results. And yes, it's interesting because the most of you who are attending this webinar haven't any experiences in designing timber in structure analysis programs. This is perfect because today we will do this with RFEM 6. Perfect. Good. So let's create a new project. So I go here to File, click here on New. This is nothing new for you because you have already, I hope so, visited the last online training about concrete, steel, also the basics of member and surface design. And here we insert the name, timber column. The type of model is 3D. And then the next thing in the add-ons, we have to activate the timber design. And also here in the standards, we see, okay, timber design according to Eurocode 5. So I will do the Eurocode 5 because I am from Germany and I'm familiar with the Eurocode. The national annex is the European one. and it is important for the timber design to select the corresponding standard group of the load case classification and combination wizard. And here we have timber. So with regard to the serviceability limit state designs, the standard with the corresponding addition timber must always be selected. Yeah, so remember this, and because then you can adjust here also some other settings like these ones, and this is important here according to this Eurocode. So remember, load case classification for timber design, always choose here this one. Okay, so much to that. I click on OK, and now we start on a new working area. So the next step is the creation of a cross section. First of all, I will change here maybe the work plane and the XZ plane, and I go here to new single member, go to the tab section, and I want to create a new cross section. So I create a new cross section, click on this icon. I choose here this massive rectangle. You can also go to the cross section library and choose here this one. It's the same. Okay, the geometry is 160 millimeters as width, and the height is 200 millimeters. And the next part is the definition of a material. Here we have a normal C24. So I go here, create a new material, enter here the name C24, so softwood. I click on OK. And now you see here this new cross section with this material. You can also go here to the material properties. See here the material values and also the timber design factors, partial factors, and also here these modification factors according to the Eurocode 5, and also depending on the different service classes. Okay, good. So much to that. Let's go and click on OK. And I will draw now the column 4 meters along the global z-axis, but in the opposite z-axis, because I want to have this column 4 meter high. So I enter here the value of 4 meter. And this is almost everything. Now I can change the work plane again to the Y and X plane. I see here this member. And the next thing is that we give this member some support, some nodal support. So I choose here this node at the bottom, click on node in order to also activate the rotation around the x-axis. I have to adjust this nodal support. So I go here to create new nodal support, and I activate also the rotational Vx around the global x axis. I say OK. I say apply. And now I will do the same on the top node. I click on OK. And there I create also a new nodal support where we activate the V axis and also the translational forces in order to get here some horizontal forces for the case when the column goes into that direction. Okay, I click on OK. OK again. So now we see it here like that. And the next thing is the loading. For this easy case, we have a kind of design load in one load case. So in this case, we use here this load case self-weight. In order to consider this also as load combination, we have to do some further steps. So first of all, we can here define in the action category the different action categories, and depending on that, also the load duration. And for our cases, we use here this medium term. This is typical for the Eurocode 5, that for timber structures, you have also to consider here this load duration. And then the next thing is, let's go back here to base, and I don't want to consider any combination wizard, so I will create my own load combination. So I go here to design situation, delete these serviceability states, and go here now to load combination and create my own load combination, because through the load combination, he will consider this for my design. So now I have to assign it. So which load case? I said this load case with a specific factor. And because I already say to my load case, this is the design load, I say also here the factor should be 1 for the load combination. Okay. This was everything. Maybe let's do the, we can leave it like that because it does not make so much sense. So now we apply the load. We click here on new node load for self-weight. And here we enter the design load of 150 kilonewton. I choose here this upper node. And now we have it here. Okay, now in order to perform a kind of timber design, we have to assign also some buckling lengths. So by clicking on this member, we see here also the design properties depending on the activated add-on timber design. So when I activate it, I see here 3 more registered for the definition of some design properties for the timber design. So let's go to the first one, to the design types. And in order to consider the stability proof, I have to go here to the effective lengths, and here I have to assign some effective lengths for the equivalent member method. This is the method of for stability cases. So I create here a new one. What I want to consider is only the flexural buckling, because for this simple column we only consider flexural buckling because of the compression forces. We don't have any bending moments, so we can neglect the lateral torsional buckling. So let's go here to nodal support, and here for this case I want to have here effective length factors. Here in this case I can choose here the factors, and for this reason I will leave it here like that. I can show me this also here in this example. When I enter here also, so when I want to release it here and I increase the factor and for S2, then it will be interesting what will happen. So let's do it maybe in that way. So this is the first time. So I have here a kind of release in the Y direction, also here too. I say okay. I click on OK again. So, and we can also show us these types of, I'm sorry. And we see it here like that. And now we can calculate it. Okay, so now let's go to the results of the timber design. And as we can see here in the overview, we have here this design check type stability, and the design check ratio is more than 1. So the design is not fulfilled. So I can also go deeper into the whole design check, double clicking on one of this design and see here the whole calculation of this specific design check. It's very interesting because then you can also compare it with your hand calculations of your study or of your exercises, and it is very nice to have it and to compare it with your results. So, and as we can see here, we have here a quite high buckling length, and this is also the reason why this proof is not fulfilled. Therefore, I will change it and you will see what will happen. So I go here to design type, modify it, and say here 1. Say okay again, and now let's do the timber design again. And now you see, okay, actual compression with buckling about both axes is fulfilled, and it works. Okay, maybe a few words to the other things here. We have also the possibility to set up the service classes. Here you can see dry, moist, wet, with different temperatures and their relative humidity. You can set it up. You can set up it here also as property of a member. And we have also the design configurations for the ultimate configuration. And here it's very interesting to you can also reduce the stiffness according to this Oracle. When you are in Germany, for example, this is possible. Reduction of stiffness with the coefficient 1 divided by 1 plus k def. Yeah, this is possible, and this is normally also done for, I can show you this. This is also done for service classes 2 and 3 according to this standard. Okay, so much to that. And this was our first example of the timber column. So now I have 3 examples more regarding the timber design. So let's do the next one, and this is this one, the whole definition of design supports. So I'm sorry, I'm a little bit sick, but this doesn't matter for this training. So we have here this timber slab with different timber beams and also with a main girder here. And what I have here are some design supports. What are design supports? Design supports have in general 2 main functions. The first function is the definition of boundary conditions for the design compression perpendicular to grain direction. Yeah. And the second one is the segmentation of the member or set of members for the deflection design. So what do I mean is easy. I go here to the design support, and here you can see the design support of already 3 created different design supports with timber. And when I do this design support, then I can also consider the proof of the design compression perpendicular to grain direction. Yeah, this is important for the timber design in order to see here the support compression here in this bearing support. This is important in order to prove it for the timber design. So, and this is also part of the member. go here to the design supports and deflection, and here you can see the design supports on the left side. So in order to consider the compression perpendicular to grain direction, and also you can check here some additional settings for the deflection analysis. This is also pretty interesting. Okay, so much to that. Now I would say let's calculate everything. Go to the timber design. And as you can see here, okay, this design check is not fulfilled. Why? Because of the section-proof design support in plus z-axis. So this compression perpendicular to grain according this standard chapter is not fulfilled. And what can we do for that? This is very simple. We can increase the support length, for example. So let's do this. I increase the support length, so we get a bigger and more surface for the supports, and this means, okay, this will be a little bit longer, and then the pressures of the timber beam have more place to distribute. I click on OK. I say yes. So there we have to recalculate it again, timber design. And now we can see here, design ratio, that this section-proof design support is fulfilled. We can also double click on that and we can see, okay, it works. Also here with this, how it's the name, effective contact length parallel to grain. Here, this is these 80 millimeters, what we have increased in order to get a good ratio under 1. Okay, so much to that. So remember, design supports for the proof compression perpendicular to grain direction. And now the next one is I can also activate some some notches or also some openings in this timber beam. And these are some local cross-section reductions I can consider for my timber design. And how to do this is easy. I click on one of this member, and as you can see here, design properties. I'm sorry. Design properties, and the parent member is in this case a set of member, in this case continuous member. So every member can also be part of a kind of overall member, in this case this continuous member, and I can click on that. So this is the member set. Member set is a kind of summarization of several members and can be identified as one member. So as you can see here, we have here also this design types and also here a kind of local section reduction. And this is something I want to create now. I click here on reduction type. I can select here start notch, inner notch. So for openings in the middle of the beam or also end notch. I choose here this start notch. The notch length is, for this case, the length of my half of my design support. So in this case, 0.04 meters. The orientation is a depth. We have also width, but in this case, depth. And the reduction of depth is, in this case, 100 millimeter z-axis. And I want to activate the notch at the support in order to consider it for my design. I say okay. I say yes. And now you see here this notch. Yeah. It's the middle of our design support. And now let's calculate it. I say, okay. I can see here this also in the whole rendering when I remove this object by visibility. Oops, sorry. I see it here. And now let's calculate it. Check the results. And a nice thing is that I can click on one of the member in the working plane, and I can see also here the design ratio by the design situation. Also here the relevant design check, section proof, not at support, and this is the result which is relevant for this one. Okay, so much to that. So now you know what are design supports, how can I consider different local cross-section reductions, and in order to summarize now the chapter, I have prepared a poll for you. Please answer this one. Okay, I will show you the results, and the most of you have voted the right result. So in order to carry out the check pressure perpendicular to the grain direction, you need design support, and therefore the answer with true is the right one. Okay, good. Now let's continue with another example. I will go here to window and choose here this Duopitch roof. So we can also consider Duopitch roofs for the timber design, and therefore we have also a specific kind of member. So for this simple example, I have already created some materials. So we have here a glue lamp timber with 24 Newton per square millimeter as bending stiffness, and also here this sections. So we have here a kind of starting section and also the section in the middle. And what we do here right now is that we that we go here to create a new single member. Go here to section, and now we have here in this field a kind of distribution type. And normally we use this uniform, but we can also consider here this saddle in order to create here this Duopitch roof. So I create here this saddle. My alignment is at the bottom, and the middle node is in the half. So I go here to 50%. And my member start is this cross section. And at the internal point K, it's this cross section. So this is everything. The member type is in this case beam. I click on OK. And my member length is 24 meters. I say 24 meters here. And yes, now we have it. So the next thing is that we go here and create some nodal support. So in this case, I choose this one. And for this one, I choose the other, sorry. The roller support. Yeah, and the next part is the division of this member into internal nodes. Double click on that. And now we can also create here nodes or members. You can see here we have already created one node of on member. And by clicking with the right click on members and go here to divide member and intermediate nodes, I click here on 5 and activate this option, create on member nodes without dividing member. So we will get additional nodes on member without dividing this member into several members. I click on OK. And now you see here these nodes, so these internal nodes. And as you can see here, we have here also one node more. So I can delete this one. I say OK. And I can also delete this. Okay. The next part is the assigning of some lateral support for the design. No for the global model, but for the design. So double click on that member, nodes on member, and here I see also the design types. As effective length, we have now one really nice possibility in RFEM 6 is that we can consider here this flexural buckling. And because we get also some bending moments, we have also to consider lateral torsional buckling. And now we can consider these node sequences. Now we have only the first and the end node by choosing here this member, and all these internal nodes are also detected automatically. Now I can activate the lateral support in the Y direction. We can take a brief look how it looks like. And you see here, okay, they are located here. And don't wonder, and the current position of these lateral supports have no impact for the design of these timber beams, because you determine the elastic critical moment for the lateral torsional buckling analytically. And when you consider here a kind of eccentricity, then it can be possible that it has an influence. But for our analytical approach, we don't have here any influence. I say okay. Okay again. And now it looks like that. Yeah. And in order also to see the statical system, you see it here like that. So we draw this whole Duopitch roof beam from left to right with a straight line, but the statical line, and this is also the reality, has a little bit eccentricity. And this will be also the reason why we will get here also some normal forces. Okay, so let's continue. Now we have to assign, we have to apply some loads. So first of all, I have already created some load cases. They are in German. This is no problem. I can change them also into English. So south weight, permanent, and snow. And for each load case, I want to consider a load. So I say, okay. And a very nice thing is that I can now apply the load, remain in this dialog, and only changing the parameters for the load and also the load case. So in this case, I have here this load magnitude. I choose here this number. I say apply next. The same with permanent. I have here 2.7. Apply next, and the same with load case 3. I say okay. So this is wrong. I need this on the projected length, the snow load. Now it's correct. Okay. So the next thing is that we go here also to the design situations. And here I only consider the ultimate limit state. This is enough for this example. I consider also only geometrical linear analysis. So no theory second order, only geometrical linear, because yeah, the influence won't be so much. And then we have here also these two action combinations, and also here these two load combinations. Okay, so this is everything. Now we can say okay. I can say okay, calculate me please everything. So the program calculates the load cases, the load combinations, and also the timber design. So now let's take at first a look to the static analysis in order to see the results. I will deactivate maybe here the types of the beam design. And as you can see here already, we get here some compression forces. There's some negative normal forces, so compression, and this is because of this eccentricity. When you compare it with your hand calculation, you don't have this kind of static system, but in reality this is the right one. And when you do this by hand calculation, you neglect this statical line here. So this is the right one. Also take a short look to the bending moments. Looks like that. When someone is wondering, okay, hey, why I do have here this strange moment distribution, this is because of this eccentric statical line. Okay, good. So now let's go to the timber design here in the tables. We can also see here the different design ratios on members, and it's pretty nice because we see here also the stability flexural member without compression forces. We see here also the governing results, and you can also click on one of this in order to see the results, and it's pretty nice because then this is a pretty good example where you can also compare your results with the results of the structure analysis program RFEM 6. Okay, when you do timber design, then it can happen that you want to know the location of the maximum bending, the maximum stresses. So yeah, bending stresses. And therefore it's important to consider also a good member division of the internal FE nodes. Where can you do that? You can go here to calculate mesh settings, And here you see the members. I have increased it to 24 here and also here. So these are the default settings. And when I do here some strange things like this, so I decrease the number of divisions of the FE nodes for the member. You can also show you the FE mesh on members. We have to generate it. Then you see it here. And they are depending on this one, on the nodes on member. If I wouldn't have them here, it will be less FE nodes. So I calculate the whole thing again, and now you can also see it in the results and also in the timber design. So look at this strange moment distribution and also to the timber design. Yeah, looks a little bit strange. So this can be the reason why you should not have here this FE mesh of the members, not two cores. Yeah, so remember that, not two cores of the member refinements of the FE mesh, because you can neglect or also you can underestimate some things. So please remember that, and now we increase it again to the default settings, and they are normally mostly okay. Okay, good. So one more thing, we have also, in order to get to know, okay, what is your cut to grain angle, you can also go here to the section proof, and now you see here also in every proof the cut to grain angle, and this is here 5 degrees, and also with that design check, with that section proof. Okay, you can also skip between two load combinations and also go here through different member locations. If you want to have it at each meter, for example, you have to increase here, going to mesh settings, members, number of divisions for result diagrams, 24. Calculate it again. And now you can see it at each meter, like here. Okay, so much to that. This was the third example. In order to summarize this a little bit, I have prepared a poll for you. Okay, the most of you have voted. I share the results. And the question was, okay, to determine the location of the maximum bending stress, it is advisable to use a member subdivision that is not two cores, and this is correct. Yes. So the most of you have chosen the right result. Okay, good. So now let's go to the last example. Now we will model truss with the help of some member representatives. So I go here again to the timber truss beam, or timber truss means the same. And again, here I have already created some materials, some sections, and also some load cases with the German name, but we can also change it to English, or you will learn today a little bit German. So Eigengewicht means self-weight, Ausbau is a permanent load, and Schnee is snow. Okay, good. So the first thing what I want to create is the upper beam, so the upper girder. Before we do that, I want to show you here in the base data that we have also the option to use member representatives. What are member representatives? They are templates for 1D objects having identical properties regarding material, cross-section, member type, and length. So these representatives can be understood as member templates. And they facilitate the evaluation and documentation of results. So they will help you to do this much faster and much better. And since only the member with the governing internal forces and moments of all similar types is analyzed, member representatives provide a good overview in both the program and the printout. I will show you this afterwards. And here you can see also how the member properties are considered for member representatives. So they have member representatives are recognized when they have here these 5 properties: same, materials, sections, line types, member types, and length. Next to that, you can also add here some more properties, but for our case, this is completely enough. Okay, so now let's do the upper girder at first. So I create here a new member, go here to section and choose here this one with this glue lamp timber. The member type is beam, this is everything. 40 meters as length. Now you see here already this red node in the middle, and this stands as, or this stands for the member representative. You can also, let's show you this one. I will divide this member in the middle, so divide member, because I want to have here 2 additional beams. And this middle node, I change the global Z coordination to -1.8 meters. I say okay. Now we have it like here. And I will create here also a kind of hinge, a moment hinge, in order to build here a kind of 3-hinged frame. Hinges in the end, this moment hinge. Now let's go to the upper girder, to the lower girder. It will get some tension forces, so the tension rod, you can also say to that. In this case, I consider here this cross section. And the member type is here in this case truss. What means truss? Truss means that on both ends we have moment hinges. Okay. And now you can also see here, okay, we have now 2 different colors, the green one and the red one, and they symbolize me the member representatives. Okay, now I choose this one, right click, and now I want to divide them again into 2 parts. No, not into parts, but in intermediate nodes. So I go here to members, say divide member, intermediate nodes, in this case 2. But now I activate here this option, in order to have some internal notes. So now I have to create some filling members. I click here again on this member. In this case, again, truss section is in this case this one with a C24 as material. This is a quadratic cross section. I click on OK, and now I draw it here like that. So now we have our truss. What we do now is adding some supports. So much to that. And the next part is assigning the load. So Eigengewicht, self-weight. We can leave it like that. We only activate here the self-weight, go here to the load case Ausbau, so some permanent loading on the roof. Here we have 3 kilonewton per meter. So I go here, 3 kilonewton per meter, choose here the upper girder. I say OK, apply and next. And then I jump to the next load case, Schnee. This means snow, 3.5 kilonewton meter. And I assign it again to this member and I say OK. And now I have to change also the load direction. And this is the projected length. Okay, so much to that. Now I go again here to the load cases, and what I want to consider is here all these design situations. This is okay, pretty fine, but all these all these design situations should be combined according to the theory of first order, so a geometrical linear calculation, because then all load combination are calculated with the theory of first order. Okay, so much to that. In order to do now the design of timber, we have to give them some buckling lengths just to perform the stability design according to the equivalent member method. So I choose here now we can see here a real advantage of the member representatives. Go here to the data navigator, go here to the member representatives, and here I see this overview, and I go here to beam, and I say, okay, this beam should have an effective length. It should be considered here all these three things, and also the effective length should be here 7 meters. Yeah, 7 meters. So this is the projected length, and 2.58 means that every 2.58 meters that we have a kind of lateral lateral support. What can we consider here? And the same also for the torsional buckling, lateral torsional buckling. Say okay. The design configuration, only the standard, so I consider only here these things. I can also perform the stability design here and add some further some further settings, but for this case it's absolutely fine. Here now let's come to the truss, here to the lower truss. In this case it's absolutely not when we don't consider this lateral torsion buckling, because it mainly gets tension forces, so even this flexural buckling, normally we don't need this, but you can leave it here like that with this principal axis. I think this is enough. I say okay. And the only thing we have to do right now is also to give them a kind of serviceability configuration in order to perform this deflection here with these beam limits. I say okay. And the other 3 we can assign the effective length of the same of the truss. I say okay. Now let's calculate everything. And the results looks pretty good. Let's go to the timber design. And yeah, the results doesn't look so good. Yeah, this could be the reason why I have to check it maybe a little bit again. But now you can also see here the stability, why it is not fulfilled. Yeah, because of the stability axial compression. And we should take a closer look. Okay, what is here not okay? Yeah, just in order to see, okay, what we have done wrong. Maybe I can do a small fix here, maybe in order to, oops. In order to see, okay, what is wrong here. Yeah, this would be something I would need to know. But now you can see, okay, the stability design is done. And also the section proof, this normally works. So I have to consider also some stability for further things in order to consider this stability design. Okay, so much to that. And yeah, so now you can see it, what we have done. Also here, how we consider this timber truss with different load cases, and also for the timber design. And yeah, this was also the whole training. So I hope you enjoyed this training. I hope you have learned some new things. We are also at the end. I have one last poll for you in order to summarize the whole topic at the end regarding the member representatives. Okay, then most of you have voted. Okay, so what are member representatives? The first answer is correct. Member representatives are similar to member templates with identical properties like material or also like cross-section length and so on. And the other answer, this refers to member sets. Okay, good. So in order to say thank you, I would like to let you know, okay, it was a I really enjoyed the whole trip with you. You saw, I guess, 6 different online training about different topics, about the member design, FEA, but also some cross sections, how to define and model them. And then we gave you also an introduction about steel, timber, and also concrete structures. So now you are very good prepared for your study, and you can always refer to the solutions what we gave you in the past. And I hope you will also use our programs for your study cases, for your examples, for your exercises. And who knows, maybe we will see us in the next webinar or online training, or also at the next event on site. This would be very nice. So whenever you see a kind of Dlubal booth or a kind of Dlubal advertisement, think about this online training, think about the program, which will help you to your exercises and also to do structure analysis. With these words, I want to say thank you very much for your attention. And yeah, Jürgen, are there any things maybe to discuss or to show?
Well, actually, there are no open questions at the moment, but I think I have found the problem with the effective lengths here in the timber truss.
Yeah, this would be maybe good in order to
write this model, and you just go to member representative 1.
Yes.
And in the effective lengths.
Yeah, sorry, this was the wrong one. Yeah. Effective lengths, yes.
So have you set the absolute values down below? Because the check is set off.
Yeah, you are right. You are right. I have mixed it up. I wanted to add here absolute values. This was the reason. Oh, Jürgen, thank you very much. So
no problem.
Thank you very much. Now we have solved it. So I forgot to activate here absolute values. So we have effective length of 7 meters, and I activated here the factor, and this was completely wrong because I would overestimate this. So now let's calculate it again, and now I'm pretty sure you will see the right example, so the right results. And yeah, now now the whole design is fulfilled. Jürgen, thank you very much for this end. Okay, now you see everybody can make some mistakes. It's important to help each other in order to fix or to improve oneself. And now we have also solved this problem. So with these words, I want to say thank you, goodbye, and in these times, very important, stay healthy. Bye-bye.